In the face of deadly radiation, raging sunstorms, and asteroids the size of Mount Everest, robot space probes are opening up a whole new frontier of exploration for humankind. Right now, millions of miles away in deep space, probes on Mars and on Saturn's moon Titan may be on the verge of answering one of our most fundamental questions. Could life exist on other worlds? Since the dawn of the space age in the 1950s, man has sent over 200 robotic probes into space. Millions or even hundreds of millions of miles from home, these astonishing machines are our eyes and ears in space. Orbiting other worlds, landing on alien moons, probes have shown us the universe up close and personal. They have brought back samples from moons and comets, and even the sun itself. These are delicate, super sophisticated machines, yet they must survive the brutal battering of launch, the savage cold and radiation of space, all to help science solve the great mysteries of our solar system. Each generation of probes is more sophisticated than the last. Now, decades of design and experiment have culminated in the two most ambitious probe missions ever, set to explore the two worlds in our solar system that most resemble our own planet Earth. Mars, cold, almost airless, and flooded with deadly radiation. Yet this is one of the few places we might find liquid water, a vital ingredient for life as we know it. But safely landing two large and delicate rovers on the surface of an alien world, after a journey of nearly 300 million miles through space, is a near impossible challenge. And then Titan, Saturn's largest moon, so cold that its rocks are made of water ice, and its rivers are liquid methane. Titan closely resembles Earth billions of years ago. Reaching this mysterious world requires a 7-year journey, passing through the asteroid belt, and an encounter with Saturn's deadly rings. Scientists hope that somewhere on these worlds, they may find clues to answering mankind's most fundamental question: is there life elsewhere in the universe? NASA's plans to send 2 rovers to Mars got underway in the year 2000. Their mission, to spend 3 months exploring the red planet's surface. The mission's principal investigator, Professor Steve Squires, has dedicated 16 years of his life to making this ambitious mission a reality.
I had absolutely no idea how rough it was actually going to be.
A lot rides on this mission. 2 previous probes to Mars have failed. The first was planned to orbit around the planet. It missed and burned up in the atmosphere. The cause, a mix-up between English and metric units. Then, just 10 weeks later, they lost its sister probe.
Our mission arose from catastrophe. We had 2 missions that preceded us, Polar Lander and Climate Orbiter, that were both lost at Mars.
Squires' project is mission almost impossible. He has just under 3 years to build and launch 2 new rovers.
Either we were going to go to Mars when we did, or we probably were never going to go at all. And so we had this absolutely inflexible deadline.
The schedule is seriously tough, but the real challenges are technical. The probes must survive a bone-shaking launch, a 7-month flight, and then hit a re-entry window just 4 miles across, traveling at 12,000 miles per hour. In the atmosphere, a complex parachute system will decelerate the probes to just 12 miles per hour. They will literally bounce to a standstill using a series of airbags. Only once the protective casing opens can their mission begin. To design and build 2 Mars rovers from scratch in just 3 years is an incredible challenge. But the engineers have one big advantage. 3 years earlier, when 2 Mars missions failed, one other mission, Pathfinder, succeeded. Pathfinder was the first roving vehicle to have been safely delivered to another planet. It didn't travel far, but proved it could be done. The 2 new rovers are scaled-up versions of the original. But there's a problem. The rovers get scaled up and up. More and more instruments get added. A panoramic camera, sophisticated geological tools, a microscope, then large solar panels to power it.
When we actually got down to the business of stuffing it into the lander, it was about 10% too big. It wouldn't fit in the lander.
The team set to work to build a bigger craft to transport the rover through space to its final destination. Next, the rovers themselves must prove their worth. After 2 years of intensive design and assembly, the team get their first chance to see them in action. After so much struggle, it's an emotional moment.
To actually see a fully assembled rover come to life for the first time brought tears to my eyes. I mean, I try to be the tough space explorer guy, but that was just too much. That was an overwhelming feeling.
This is the Sandbox, a simulation of Martian terrain at NASA's Jet Propulsion Labs in California. To collect the samples and images the team needs, the rovers must travel miles over a harsh terrain of dust and rock in temperatures as low as minus 190 Fahrenheit. Key to their survival is an innovative wheel design that should help protect the rover's delicate instruments. The spokes have a unique spiral pattern to absorb shock. They are made from a special material called solamide, which can flex at extremely low temperatures. Cleverest of all, rather than using springs, the rover bends at its joints like human limbs. This allows the probe to climb over rocks bigger than the diameter of its own wheel. With the rover's design now set, the team at last knows how much the vehicle will weigh. With just 7 months left, it's time to finalize the design of the parachutes. They must be capable of opening in the thin Martian atmosphere at supersonic speeds. Lead engineer for this phase of the mission is Adam Stelzner.
At about 1,000 miles an hour, we open up a parachute. The parachute takes us down to a couple of 100 miles an hour.
The parachute is a disc gap band design with 2 key parts. The upper part, called the disc, inflates to the shape of an upside-down bowl 30 feet across. This provides most of the drag. The band, suspended below the disc, helps to stabilize the system. The design must be perfect, and for that, they need to test it. The trouble is that simulating the immense speeds that occur on entry to the Martian atmosphere simply isn't viable. To compensate for these lower speeds, they must add an 8,000-pound weight, 4 times heavier than the actual spacecraft. The system must work perfectly, first time, 100 million miles from home. The test weight was lifted to around 3,000 feet by a Chinook helicopter.
The first big full-scale parachute test. We feel very confident, everyone's good, it's a beautiful day.
On the ground, the engineers watch confidently as the helicopter releases the giant dart. Then, disaster. The parachute shreds dramatically. It will never be strong enough to use on Mars.
There's a pit in your stomach. You're trying to search through your mind as to what went wrong.
They can't increase the size or strength of the parachute. With every pound of weight a premium on the spacecraft, it needs to fit inside a 10 by 17-inch bag. So they create 3 new designs, with different fabrics and different sized discs and bands. To save time, They test them in the biggest wind tunnel in the world, housed at NASA's Ames Research Center in Northern California. Huge fan turbines simulate high wind speeds by sucking air through the vast chamber. With the turbines on, the newly designed parachute is fired from a mortar. This time, the parachute fails to open properly, flapping half open, half closed, an unusual phenomenon called squidding. It's unexpected and disastrous. After the test, they discover the problem. The main vent hole at the top is bigger than it should be. With time running out, they shrink the hole by hand and try again. At first, it begins to squid, but then suddenly, it opens. At last, they have a parachute that can slow the spacecraft in the thin atmosphere of Mars. By May 2003, the rovers and spacecraft were nearly ready for launch. But then a problem develops that threatens the whole mission. Small bolts and cables hold the rover in its traveling configuration. Now, just weeks before the launch, the team discover that the small explosive charges designed to release those bolts may be faulty.
They're little explosive devices that cause a solar panel to deploy or an arm to deploy or something that allow these things to separate from the vehicle.
If the pyrotechnic system malfunctions, the whole mission could be a write-off. The timing of discovery couldn't be worse. There are just days to go. The rocket is already on the pad.
This could threaten the whole mission. If we're not able to launch these things now, it may not make sense to ever fly them.
It's the biggest race of their lives. May 2003. After 3 years of preparation, the Mars rover Spirit is ready for launch. But at the very last minute, a technical problem could force the mission to miss its launch deadline. The design team have discovered that the pyrotechnic cable cutters that release the rover when it reaches Mars may be faulty. They can't be sure without checking. But at this late stage, opening up the rover is impossible. There is only one solution: to track down the fired pyrotechnic cable cutters used during the testing phase to see whether they were flawed. If the old ones are functional, then the team can be confident that the new ones on the rover are functional too. Kobe Boykins, a mechanical engineer, was involved in the hunt for these old pyros.
Some were at the lab here at the Jet Propulsion Laboratory. Some were at the Kennedy Space Center. Some were put away in closets. Some tests were done early enough that those pieces had been removed from the rovers early on in testing and put in a box, and that box was put in a cabinet.
With time running out, the engineers tracked down dozens of old pyros, each one being tested for the fault. They all passed. And just as they were fueling the second stage of the rocket on the launch pad, the last pyro was discovered. NASA gave the go-ahead for launch.
It went right down to the wire. There were many, many times during the development of our spacecraft when I didn't know if we would make it. I mean, 3 days before launch, I didn't know if we would make it.
Then at last, the moment Steve Squires has dreamed of for 16 years. The launch of the two most ambitious probes ever sent to Mars, Opportunity and Spirit. Their time has finally come. First to go is Spirit.
Standing there on the beach in Florida, I didn't know if we had done enough or not. I didn't know if these things were going to die before they did their jobs.
Launch is a risky process. Millions of dollars of complex engineering can be obliterated in an instant.
There's anxiety, there's anticipation, there's like excitement, happy excitement and dread. It's all balled up.
The probes sit on top of almost 10,000 gallons of highly explosive rocket fuel. A rocket is essentially a controlled bomb. No launch could ever carry a safety guarantee. As the countdown begins, the engineers wait nervously.
15. Electronics go. And hydraulics go.
Gotta remember to breathe. Gotta remember to breathe.
The moment up to the point where they actually light the rocket, where the fire actually starts, you're sort of sitting there and it's sort of quiet anticipation. You're just ready for it to go.
T-minus 10, 9, 8, 7, 6 green board, 5, 4, 3, 2, 1. Hit start and liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
Load relief kick rate is in, vehicles responding. Vehicles recovering very nicely from the liftoff transients. We're approaching Mach 1.
It sounds silly. I mean, it's a robot. It's a piece of metal, right? It's not a human being by any stretch. But you develop this sort of intense feeling for them, and then, man, you put the thing on top of a rocket, and it's gone. And you realize, I'm never going to see this thing again.
And we're out there hoping it's going to go, hoping it's going to go. Boom, it goes. Glorious, you know, because it's thundering. Continual rolling thunder, the likes of which you've never heard.
A month later, Squires watches with his family as Opportunity joined its twin, Spirit. Together they begin their epic journey to Mars. But why do we keep going back to the red planet? The answer is water. Older probes in orbit around Mars have revealed telltale signs of ancient water erosion on the Martian landscape. Gullies, riverbeds, perhaps even oceans. And where there's water, there might just be life. The signs are unmistakable because they also appear on Earth. Planetary geologist Professor Phil Christensen studies how water erodes our planet's surface.
From orbit, we can look down from above and see the entire planet. So just like in a helicopter, you get a totally different view than if you're down walking on the surface.
This aerial view shows clearly how water erosion carves the features that you see in Arizona today.
On Mars, the landscape is very similar to this. Some of the canyons form by very rapid floods, where canyons larger than these can form in a matter of days.
On Mars, these features formed millions or even billions of years ago. They raise a tantalizing possibility. Both rovers will land in areas that might once have been lakes. Their mission is to learn more about the way water may have shaped the red planet. They may even find clues that will help future missions solve the biggest question. Has life in some form ever existed on Mars? First, the rovers need to get there. They must complete a dangerous trip through space of almost 300 million miles. The first 3 months of the journey to Mars goes as planned. Then, Mission Control receives some alarming news. Scientists at the U.S. Space Environment Center have just recorded a massive burst of solar radiation from the sun. A solar flare bigger than any witnessed in history is on its way toward the delicate probes. Solar storms are deadly. They can knock satellites back to Earth and even fry electrical grid systems.
The biggest solar flare in recorded history happened while we were on our way to Mars. It's just the kind of luck that we had with this mission. If there could be plagues of locusts in space, it would have happened to us.
The probes navigate by recognizing star patterns. Squires and his team fear that the bursts of solar radiation will be interpreted as stars by the probe's navigation system. This could be disastrous. The probes could go off course and never make their rendezvous with Mars. To solve this, the mission controllers switch to a backup navigation system that uses the sun itself. Their other worry is that the solar flare will damage the probe's computer memory. All the team can do is wait. After the storm has passed, the team reboot the computers to check for damage. To their enormous relief, the memory is intact. The probes have survived the biggest solar flare ever recorded.
It turns out that our spacecraft was more robust than most.
After almost 300 million hazardous miles, the first probe, Spirit, now faces the most dangerous part of the mission, landing. It's relying on yet another novel technology, airbags. These will envelop the whole craft and cushion its landing. Re-entry and landing is the shortest phase of the mission, yet a single failure, a single miscalculation, and the entire mission is a write-off.
You hit the top of the Martian atmosphere going 25 times the speed of sound. 6 minutes later, you're on the surface. It's a hell of a ride.
It's been called the 6 minutes of terror.
On January 25, 2004, the spacecraft hits the Martian atmosphere 20 times faster than a speeding bullet. Friction slows it to just 900 miles per hour. It's time for the parachute to deploy. But has it opened correctly? In mission control, they nervously wait for a signal. Minutes pass. Then, at last, a faint signal. The lander is now descending on a cable, hanging below the entry vehicle. Next, they must wait for the airbags to deploy and stay intact.
It has to be able to take an impact at freeway speeds running into a pile of rocks.
Finally, seconds before landing, reverse rockets will fire to soften the impact. Once again in mission control, they wait for a signal. The craft will be out of radio contact until it reaches a standstill.
And all of a sudden it's bouncing and spinning and it's rolling, and you lose any capability to communicate whatsoever.
So we lose contact. You really worry whether the spacecraft has survived.
16 years of work hangs on whether in that next moment you get a radio signal or you don't.
By now, 100 million miles away on Mars, it's already over. The probe is either safely down or it's crashed. A signal is either traveling through space toward them or it's over. All the team can do now is wait. The space probe has landed on Mars after a terrifying deceleration from 12,000 miles per hour to 0 in 6 minutes. In NASA's mission control, they're waiting for a signal to hear whether it's survived the entry, descent, and landing phase. Nervous minutes pass. Finally, at 8:51, the rover makes contact with them. Spirit phones home.
An interplanetary hole-in-one, without a doubt.
But there is still one more obstacle before the probe can start its work. Would the cable cutters that nearly grounded the probe work when the explosive bolts fired? Or would the most complex robot vehicle ever designed be trapped on its lander for the rest of time? If everything works the right way, the rover unfolds itself, deploying its solar panels and panoramic camera. The rover then sends the first pictures back to mission control. Three hours after landing, the images arrive. They are the first concrete proof that the rover is operational.
I'm sorry, I'm just blown away by this. I will attempt no science analysis because it looks like nothing I've ever seen before in my life.
But for me, it was just this immense burden being lifted from my shoulders that we would never get to Mars. You know, here was a signal from our vehicle from the world that we had built it for the first time.
The human species got a new definition of Mars that evening. And to see those images the first time they come down, that I'll never forget that.
The very best moment of the whole mission was that first moment when we had 6 wheels in the dirt on Mars. That, to me, was the triumphant moment.
Spirit's sister probe, Opportunity, lands safely 3 weeks later. Against enormous odds, Squires and his team have landed the 2 largest and most complex rovers ever sent to Mars. The mission, to search for signs of water, has begun. Now the rovers must contend with the harsh conditions of Mars: dust storms, rocks, and craters. Avoiding all this falls to rover driver Scott Maxwell.
I have the greatest job in 2 worlds. I come in every day and I look at pictures from another world that nobody's ever seen before. It's very much like a video game. And we have a 3D copy of the rover that we put down inside that video game, and we drive it around.
Every evening, the driving team uploads the commands for the day to the rover's onboard computers. The sun gets strong enough to power the rovers for just 4 hours every day. During that time, they can travel up to 330 feet. But mostly they don't travel that far. They find an area with interesting rocks and soil, then stay to explore. Cameras on board the rovers help them avoid obstacles like rocks and craters.
As they're driving along, they can take pictures of the world and reason about what's in it. They can figure out what the world looks like in 3D and find a safe path.
Only 8 days into the mission, Opportunity rover comes across some strange rocks. They are small and perfectly round. The team nicknamed them blueberries. On Earth, blueberry-shaped rocks normally only form in liquid water. Could these be proof that there was once a lake here? Geologist Marjorie Chan believes so. Before the mission even began, she had predicted that if water once existed on Mars, the probes might find formations of this kind.
When the rovers sent back those first images from Opportunity, we saw those balls and we just went crazy.
The team is delighted. The mission to search for signs of ancient water is bearing fruit. Then comes even more evidence. The rovers discovered 2 minerals, goethite and jarosite, which could only be formed in the presence of water. After 4 decades of looking, they now had hard evidence. Groundwater did once flow over Martian rocks.
Oh, I think the evidence is overwhelming that they have evidence for water on Mars.
On Earth, water means life. If there is still water flowing on Mars, who knows what future missions might find. But water alone is not enough to get life started. That requires a complex soup of organic chemicals as well. On Earth, life started just under 4 billion years ago, and since then, our planet has become a very different place. We can't go back in time to study the conditions on early Earth, but we can still study those conditions today on another world. In the early 1980s, the Voyager probes passed Saturn, taking the first close images of Titan, its largest moon. Measurements revealed that maybe Titan's thick orange atmosphere could contain the chemical precursors for life.
In some respects, Titan's atmosphere now is like Earth's atmosphere was perhaps 4 billion years ago.
Here, tantalizingly, sitting in our own solar system, was a moon very much like early Earth. But to see how life could have started, we have to go there. If landing on Mars was hard, landing on Titan could be impossible. Saturn's moon, Titan, is the only moon in our solar system with a planet-like atmosphere. But until 1980, no one knew what that atmosphere was made of. That changed when the Voyager 1 probe flew through the Saturn system and made an astounding discovery. Titan's atmosphere contained organic materials, a lot like the ones that eventually formed life on Earth. Could Titan be at the same stage in its life that Earth was around 4 billion years ago?
Going to Titan, in some respect, is like time travel.
But reaching Saturn's mysterious moon is a challenge far greater than any mission to Mars. Getting to the red planet takes 7 months. A mission to Saturn takes 7 years, and it must negotiate not only the asteroid belt, but the 165,000-mile obstacle of Saturn's rings. In 1990, the Cassini-Huygens spacecraft was born. It's one of the most ambitious missions ever to our outer solar system. The mission came in 2 parts. The Cassini orbiter, built by NASA, will take the most close-up images of Saturn's rings. Traveling with the orbiter is the Huygens probe, designed by the European Space Agency. This will touch down on Titan, the first probe to land anywhere in the outer solar system. Professor John Zarnecki of the UK's Open University is one of the lead scientists on the Huygens probe.
Titan is halfway across our solar system. So we really were, I would say, even a little bit crazy ever to take this on.
Another member of the team has been waiting 20 years to see below the orange clouds of Titan. Professor Jonathan Lenine of the University of Arizona.
To completely understand Titan, to see what was underneath this interesting organic-rich atmosphere, it was necessary to send a probe and an orbiter.
For the design team, creating a probe for Titan is a prodigious challenge. Titan's atmosphere is so thick that we cannot see through it to the surface. Prior to landing there, we cannot even be sure what Titan is made of. Professor Zarnecki and his team design a small spike that would penetrate the mysterious surface on landing. The spike is the very first instrument to touch the surface of Titan. It sends its data back to Earth for analysis. In the laboratory, scientists compare the electrical signature of different surfaces, some soft, some hard, giving them a wealth of data.
We didn't know if it was solid or liquid. It was that bad, our understanding or our knowledge of the surface. We had no idea if we'd float on liquid methane or we'd thud down onto a hard, icy surface.
On October 15th, 1997, after 7 years in construction, the Cassini-Huygens probe is ready for launch. The spacecraft is enormous, the size of a school bus. At the time, it took the largest rocket in NASA's arsenal, the huge Titan 4B Centaur launch vehicle, to send the probe into space. The rocket weighs 1,000 tons. It's the height of a 22-story building, and at 4:43 in the morning, the final countdown begins.
T-minus 10.
Across the world, 8,000 engineers and technicians hold their collective breath.
About 12 minutes.
The previous launch of a European space mission called Cluster saw the rocket explode shortly after takeoff, destroying the $500 million spacecraft and shattering the dreams of hundreds of scientists. All the team can do is watch and pray. Professor Marty Tomasco of the University of Arizona built the camera that would take the first pictures of Titan's surface.
It was only about the 4th launch of a Titan IV for a civil space mission, and I believe the launch before us blew up on the pad.
I was such a basket case during the Cassini launch. Many people have lost spacecraft, payloads, work because the rocket blows up.
5, 4, 3, 2,
1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn.
Right on time, the rocket takes off.
Pitch program is in, roll program is in.
The launch goes without a hitch.
We have cleared
The rocket rises high above the platform. Cassini's perilous 7-year journey to Saturn has begun.
Turn is speed separation.
The spacecraft uses the gravitational pull from Venus, Earth, and from Jupiter to gain enough momentum to reach Saturn. When the probe approaches a planet, the gravity of that large body takes over, propelling it past, this time faster. Engineer on flight operations on the Cassini-Huygens mission is David Duty.
When a spacecraft flies by Jupiter to get a gravity assist, it's taking some of Jupiter's momentum to speed up the spacecraft.
But along the way, there are many dangers.
There's always the chance of micrometeoroids, small dust particle grains of sand, which of course are traveling at thousands of miles an hour.
The next obstacle is the beautiful but deadly rings of Saturn. This is the largest space probe ever built. Now it must make it through an area littered with rock and ice to Saturn's moon, Titan. The Cassini-Huygens space probe is on a 7-year journey to Saturn. If all goes to plan, Huygens will be the first probe ever to land on a body in the outer solar system. For the mission to succeed, the Huygens probe must send its data from the surface of Titan back to the orbiting mothership, Cassini. Cassini will then relay the information to Earth. Before the fixed communications system can prove its worth, Cassini and Huygens have to overcome one last deadly obstacle: Saturn's rings looming on its horizon. These rings are made up of billions of pieces of rock and chunks of ice, from the size of a dust grain to the size of a house. Saturn is 95 times as massive as Earth, and its enormous gravitational field captures any passing objects into its orbit to form the rings. These rings are wide, nearly 165,000 miles, but very thin, only about half a mile of beautiful but deadly rock and ice. To reach Titan, Cassini-Huygens will have to fly right through the gap between the 5th and 6th, or F and G rings, using its main antenna as a shield. One miscalculation, and the huge probe will smash into a million pieces. June 30th, 2004. Cassini prepares to enter orbit. Millions of dollars and entire professional careers are on the line. Mission Control waits for a signal that the probe is still intact and operating. Cassini rotates its giant antenna and heads toward the gap. Mission Control waits nervously for the signal that the 6-ton, $3 billion spacecraft has survived. 19 minutes later, a signal comes through.
Johnson just reported a signal. We've survived the ring plane crossing through the F and G ring.
The probe has survived, though not completely unscathed.
The Cassini spacecraft was hit about 500,000 times as it went through the ring plane at that point. Fortunately, all of the hits were of tiny particles the size of smoke particles.
Despite the hits, the probe is still functioning. It's time for Cassini to release Huygens for its mission to Titan. On January 14, 2005, Huygens enters the thick, foggy atmosphere. On board, a camera is set to take the first ever pictures of this mysterious moon.
This literally was the culmination of for many of us, more than 15 years of work. It was success or failure in a matter of just a few hours.
I had had nightmares for many years that this just wouldn't work and we would not get a single piece of data from Huygens.
Unlike the Mars landers with their airbags, the Huygens probe has only parachutes to slow down its fall. There are 3 of them, and they should give the probe time to take the first pictures of Titan from below the clouds. But danger heightens as re-entry and touchdown approach. It will be 4 hours before Huygens can contact Cassini to confirm it is safely on the surface. Until then, the team can only hope for the best. But unexpectedly, one of the telescopes tracking Cassini picks up a signal direct from Huygens itself, just an hour after the probe has landed, 3 hours before Cassini can relay the signal to mission control. The signal is incredibly faint, but proof that Huygens is alive and well on the surface of Titan.
The strength of the signal received on the Earth from Huygens was unbelievably small. I think it's something like the equivalent to putting a mobile phone on the surface of the moon.
Huygens was alive and transmitting directly back from Titan, the first probe to land on a celestial body in the outer solar system. Huygens has survived the landing, but the real data signal is still to come.
I'd been preparing for this for many years, and I think because one always knew that it might fail, we might receive no data, I'd sort of prepared some sort of emotional barrier in case it didn't work.
3 hours later, and 7 nail-biting minutes after Cassini was supposed to transmit, Mission Control begins receiving data back from Saturn's most extraordinary moon.
Here, for about 2 minutes, were these thumbnail images of Titan's surface, the first that any human eye had seen of the surface of Titan, coming at you 1 every second. And so it was this incredible emotional experience, and people were screaming as these pictures came through for about 2 minutes.
The first pictures through are of Huygens' descent. The landscape looks similar to parts of our own planet. The camera has less resolution than a modern cell phone, yet the images are detailed enough to show a rocky landscape, but with a difference.
We're pretty certain that it's the equivalent of sand or gravel. But in the case of Titan, the sand and gravel is not made of rocky material, stony material like it is on the Earth. The bedrock on Titan is ice.
Back in space, Cassini's special infrared cameras reveal that Titan's surface has undergone geological processes similar to those on Earth, lava flows, and even volcanoes. Cassini is set to continue gathering data until at least 2008. In that time, scientists are confident they will learn new and extraordinary things about this strange world, teaching us more about the chemicals that gave rise to life here on Earth almost 4 billion years ago. Both Mars and Titan are helping us to build an even more complete picture of how our solar system formed in the first place. And there's more to come. NASA is studying future missions to Mars, including the possibility of collecting samples and returning them to Earth. There is even an idea to send an airship-style probe back to Titan to travel through its atmosphere, gathering data. Probes such as Cassini-Huygens, Spirit, and Opportunity are the pinnacle of human technical achievement. Through them, we have learned secrets that would otherwise have remained mysteries forever. And where probes go today, perhaps people will go tomorrow.
One of the things that we're doing, I hope, with this mission is exploring the next generation of scientists and engineers who are going to go to Mars and do stuff better than we were able to do it. Okay, because they saw this on television, because they saw these pictures on the internet, and they thought, hey, That's neat. I bet I could do this. I bet I could do this better.
Wherever future generations may go, whatever they may achieve, one thing is certain. Probes will go ahead of them, revealing new knowledge and new mysteries. And perhaps one day, there will even be a probe that delivers the ultimate news. We are not alone.
This is a vision of the future. A launch system that will transport ordinary people to the edge of space and back again. This spacecraft will open the universe to all. It's a dream of those who will design and build the next generation of space planes. In the very near future, spaceflight will become an everyday activity. The corridors of space will become as busy as the airways of today. The environment surrounding our Earth will become the largest construction site ever. Dozens of space stations will orbit our planet. These weightless cities will launch and maintain thousands of communication satellites and provide a stepping stone for deep space exploration. A fleet of space planes will transport passengers and cargo quickly and cheaply. As more and more space planes ferry components up from Earth for use in space, we will build larger and more complex space stations, floating gateways to the universe. But the future is already here.
It's amazing what man can do.
I'm in awe.
The awesome power, the noise, the roar. You give me the chance like that.
This is our first true spaceship, returning from the ultimate journey, a 6 million mile ride around our planet.
Gs, folks. Descending through 76,000 feet at 270 indicated. Have a good HUD. 500.
It's our supreme flying machine, the Space Shuttle. The first ever machine equally at home traveling through the vacuum of space or flying through the Earth's heavy atmosphere.
50 and 250. 30, 25, 15, 10, 5, touch. Speed brake, waiting for 179. 179, arm and deploy. Shoot. Coming. You're rotating.
It has flown over 80 missions and carried over 200 astronauts into space.
Anybody who's got any sense of adventure ought to want to fly the Space Shuttle. The rocket ride is the best ride you'll ever get in your life. You go all the way around the world every 90 minutes. You get 16 sunrises and 16 sunsets every 24 hours.
20.
Sound suppression water system activated.
15.
And Genesis computers now controlling.
Last check was like 3 foot C's and maybe 9.
T-minus 12, 10, 9, 8, 7. We have a go for main engine start. 5, 4, 3, 2, 1, and liftoff.
To break free from the Earth's gravity, the shuttle must use giant rockets to propel it to a speed of 17,500 miles per hour, 10 times faster than a bullet. Once in orbit, its engines must operate in an airless void where there is no lift for wings, no oxygen to burn. The shuttle has to protect its crew from the most hostile surroundings ever explored. On its return to Florida, it crashes through the skies 50 miles above Houston. It must shield them from an atmosphere whose friction would burn them to a cinder in seconds. The dream of building a space plane like the shuttle has existed almost since the earliest days of aviation. As far back as 1929, German carmaker Fritz von Opel piloted a rocket-propelled glider nearly 1 mile in a flight that lasted just 75 seconds. It was the birth of the rocket plane.
Fritz von Opel tries out the first rocket plane.
In less than 4 decades, this primitive machine would evolve into an aircraft that could take man to the outer edge of the atmosphere. By 1967, the X-15 was rocketing its pilots to a height of 300,000 feet, almost 60 miles high, halfway to orbit. Touching the very edge of space, these pioneers of aviation were almost the first astronauts. But the technology needed for a plane to leave the Earth and return safely was still out of reach. The urgency of the 60s space race demanded a far less subtle approach: massive force. In 1969, NASA celebrated its greatest triumph as it landed a manned spacecraft on the Moon. Even as its astronauts explored the lunar surface, NASA's giant rocket program was already in danger. The giant Saturn V wasn't reusable. The cost of building a new rocket for each mission was simply too great. NASA has continuously experimented with other rocket systems in a quest to find a cheap launch vehicle that could be used over and over again.
9, 8, 7, 6, 5, 4, start check engines.
The future of spaceplanes belongs to the descendants of this, the first reusable rocket craft, the DC-XA. Operated by only a handful of technicians, this test craft is one of a number of designs that have paved the way for routine and affordable space travel. Lifting off under its own power, The DCXA has no throwaway boosters or stages like conventional rockets. Its unique propulsion system allows it to maneuver and fly in any direction. Constructed from super lightweight materials, almost 90% of its launch weight is fuel. At the end of each flight, this remarkable machine makes a spectacular return, landing on its tail in its original takeoff position. The DCXA has provided vital information in our search for the space plane for the 21st century. Its first successor is Venture Star. Fully reusable, Venture Star will operate like a normal airplane inside the Earth's atmosphere and like a spaceship in orbit. Planned to be operational by the year 2004, Venture Star will begin a new era in commercial space transportation. Fitted with a new system of thermal protection and a new type of propulsion, it will take off and land under its own power. Each craft will have a turnaround time of only 7 days. Best of all, it will operate at 1/10 of the cost of current launch systems. Another design for the 21st century is the mag lifter. It's filled with people and cargo, not fuel. Present launch systems have to carry all their fuel and power with them. With the mag lifter, the fuel can be left on the ground. Future spaceplanes like this will use the incredible power of an electromagnetic field to help them accelerate to launch speed. But for the moment, our only operational spaceplane is the Space Shuttle. Today, there are 4 orbiters in NASA's fleet: Columbia, Discovery, Endeavour, and Atlantis. Each one can be used numerous times. They can't launch on their own, but they can glide back to Earth. NASA's shuttle fleet has flown more than 1 billion miles and has delivered more than 60% of the world's total payloads into orbit. Hundreds of tons of cargo, satellites, and communications equipment. In Earth orbit, you don't feel gravity, so shuttle astronauts can perform experiments impossible on Earth. In this unique, weightless laboratory, scientists, engineers, and doctors have learned how to handle zero gravity. But to fly to its destination in space, this vulnerable spaceplane, no bigger than a small commercial jet, must survive extremes that no aircraft in history has experienced.
Booster ignition and liftoff of Endeavour in pursuit of a Japanese satellite.
Houston, controlling. 17218, interim. Roll program, Houston.
There has never been a flying machine that takes the pounding that the orbiter does.
A little Cessna goes from 0 to 150 miles an hour. The Space Shuttle goes from 0 to Mach 25. You literally sling it to about 18,000 miles an hour. There's some risk associated with that.
Okay, ready. Cabs in, visors down, CO2 on. Start with a shake of your life here.
Waiting to be blasted into space, The astronauts in their small spaceplane are sitting on the most powerful rockets on Earth. When the main engines fire up, searingly hot gases explode at more than 8,000 miles per hour. They are so powerful, they create giant acoustic shock waves. The vibration caused by the noise is enough to shake the shuttle apart. To dampen these acoustic shock waves, at the exact moment the engines reach full thrust, 300,000 gallons of water are released into a trench below the shuttle. The vapor cloud and exhaust fumes blow out more than 2 miles in either direction. As the shuttle accelerates, it pushes through the dense air so fast that massive stresses build up on its light aluminum frame. To prevent it from disintegrating, the main engines are throttled back until the shuttle reaches thinner air in the upper atmosphere. When the pressure reduces, the shuttle begins accelerating again, rocketing towards space at 15,000 miles per hour. After discarding its solid rocket boosters, the 3 main engines power the shuttle the remaining 50 miles into orbit.
Endeavour Houston, go with throttle up. Roger, go with throttle up.
Once the external liquid fuel tank is jettisoned, this fragile machine and its crew have survived the first leg of a fantastic journey.
Welcome to space, guys.
Time on orbit is very expensive, and so your day is packed. But if you do get a little spare time, what came to me anyway is I'm looking down on the Earth and I'm looking out the window at this black void of space and the harsh environment that we're in. What I hear in the background is the cabin fans of the vehicle. Everything is just running smoothly, and I'm thinking, what a fantastic spaceship to work so well. You don't think about what it's protecting you from.
In order to survive the extreme conditions of space, a spaceplane must create a microenvironment in which both humans and machinery can function. As the astronauts go about their tasks, a life support system automatically provides everything they need to survive. Onboard filters and air conditioners control temperature, humidity, and air pressure. An atmosphere identical to that on the Earth is produced and completely replaced every 7 minutes. The orbiter must also power its huge banks of electronics and computers. Over a 2-week mission, onboard hydrogen fuel cells generate as much energy as 10,000 car batteries. A byproduct of these mini power stations is large quantities of pure water. The crew drinks some of the water, but the rest has to be jettisoned. It spews harmlessly out into the freezing vacuum of space, where it drifts away as tiny particles of ice. The shuttle must also carry the power to maneuver itself in this weightless environment. It is equipped with 44 small thruster rockets in clusters around the nose and tail. They produce tiny amounts of thrust, but in space there is no friction, no resistance. This small ejection of gas is enough to give the shuttle a powerful kick. But this propulsion system is also highly sensitive. Firing its thrusters in short bursts, the shuttle can move forward or backward and turn 1 inch at a time.
Current distance is 104 feet.
This remarkable precision enabled the shuttle to rendezvous and connect with the giant Russian Mir space station as they both sped over the Earth at 18,000 miles per hour. This spectacular meeting was not just a publicity stunt. It moved us one step closer to the building of the next generation of space stations, in which we will live and work. But this wasn't the only instance when the shuttle's intricate docking abilities have been put to the test. Its most spectacular mission was as a breakdown truck to capture and repair the stricken Hubble Space Telescope. Once it has completed its mission in orbit, the shuttle must survive its toughest test, a return journey of over 12,000 miles in less than 1 hour. To begin its perilous journey back home, the shuttle first must slow down. With one large burst of thrust, the shuttle drops into a lower orbit. It's on its way home. With no engines to regain height, there's no turning back. The shuttle is positioned nose up, ready for re-entry. The crew has just 30 minutes before they hit the upper atmosphere and encounter a wall of fire.
What the orbiter has to go through is unlike anything that's asked of any other flying machine.
Your feet are literally in the pilot's seat a few inches, or not much more, from 3,000 degrees or close to it.
It's like trying to fly a normal airplane through the middle of a volcano and have it come out of the other side in one piece.
Ever since the beginning of manned spaceflight, the danger of re-entry has been a constant problem. The underside of early capsules used in the Mercury and Apollo programs were covered in a thick, heat-resistant resin. This protective layer was designed to burn and break away, providing just enough protection for the crew to survive re-entry. But for a reusable spaceplane to be a success, we need a reusable heat shield. For the shuttles to survive up to 100 re-entries, they're covered in a layer called the thermal protection system. Early wind tunnel tests showed that during re-entry, the temperature would vary enormously across the orbiter's surfaces, requiring a different type of protection for each area. Captured by infrared cameras during a night landing, the nose cone and leading edges of the wings were seen to glow at temperatures hotter than molten lava. To resist these extremes, these surfaces are made of a solid block of reinforced carbon, capable of withstanding temperatures of 3,000 degrees. The upper surfaces of the fuselage don't experience such high temperatures. They're covered in soft cloth blankets made from 90% glass. Handmade in a sewing shop at NASA, over 2,000 blankets are used on each orbiter. But it's the belly of the shuttle that is the largest area in need of special protection, provided by over 25,000 silica tiles. No two tiles are alike. Each one is designed and measured to fit exactly the contour of the shuttle skin. One by one, the tiles are painstakingly glued into position. This special silicon-based adhesive remains flexible from 0 to 3,000 degrees. If it became too brittle, the tiles would break off. These tiles are so efficient at removing heat that they can be taken from an oven at 2,000 degrees and held by bare hands after only a few seconds. In the first shuttle flight, a few of these tiles fell off. It caused some damage, but the shuttle got safely back to Earth. Each tile weighs just a few ounces and has a soft, foam-like structure inside. This fragile outer skin of tiles and blankets is all the shuttle has to protect it through its fiery return to Earth. The shuttle drops from a height of 120 miles down to 75 miles, where it slams into the atmosphere at nearly 16,000 miles per hour. The crew is strapped into their seats, in pressurized suits, just in case anything goes wrong. Outside, just a few feet away, their machine begins to take the ultimate punishment. As the spaceplane screams down into the thicker atmosphere, it collides with trillions and trillions of tiny gas molecules. It hits them so hard that it creates a glowing plasma of electrically charged gas particles around the shuttle.
And I can see the plasma just building and collapsing in a bright white flash down the middle of the vehicle. This plasma is crazy. It's like little pieces of vehicle flying off in front of it there.
Within the plasma, the shuttle is traveling in a fireball as hot as the surface of the sun. To survive re-entry, the orbiter must slow down even more. It utilizes the drag of the upper atmosphere to reduce its speed by flying a series of giant S-shaped turns. 20 minutes from touchdown, the friction on the shuttle's skin reaches maximum, scorching the protective tiles to 3,000 degrees Fahrenheit. When it finally emerges from its fiery cocoon, the shuttle is on the final leg of its journey. Still over 500 miles from the runway, it will cover this distance in less than 10 minutes.
.2 Gs, folks. Descending through 76,000 feet at 270 indicated. Have a good HUD.
As the shuttle's computers sense an increase in external air pressure, they transfer flight control from the thrusters to the wings. As the wings bite into the dense air, the spaceplane becomes an airplane.
45,000 feet. Range 23 miles.
Without any power from its engines, the orbiter glides to Earth at 3,000 miles per hour. It's still traveling faster than the speed of sound, and 2 sonic booms are triggered by shock waves from the nose and wings.
Central Florida got a wake-up call. Approach and land.
The shuttle is descending 20 times faster than a conventional aircraft. Five minutes before touchdown, the commander takes over from the computers. They train for hundreds of hours for this single moment.
5 minutes.
Copy.
The orbiter hits the runway at over 200 miles per hour. The spaceplane has returned home. The shuttle program is by far NASA's longest commitment to manned flight. It is the world's most successful spacecraft, but the road to orbit was far from smooth. "4 years after the last astronauts left the moon, NASA unveiled the space shuttle. "10 years of design and 2 years of construction had gone into building it, and it had cost $20 billion. This was the first space vehicle designed to carry both a crew and a payload into orbit and fly back again. NASA hoped the shuttle would change space exploration forever. It did. The shuttle's unique design combined 3 systems in one to ensure maximum reusability. First was a delta-winged spaceplane, the Orbiter. With built-in rocket engines, it could carry a maximum of 8 crew and over 30 tons of cargo. The Orbiter weighs 100 tons and is the same length as a DC-9 airplane. The second component of the shuttle system was a giant external liquid fuel tank. Containing 500,000 gallons of liquid propellant to feed the orbiter's engines, this fuel tank would be the only component of the shuttle that would be destroyed during launch. But the orbiter's engines weren't sufficiently powerful to launch this monster into space on their own. It needed the third system, a pair of solid rocket boosters, mounted either side of the liquid fuel tank. Their enormous thrust would lift the entire 2,000-ton package off the launch pad. These 3 elements had never been tested together. The shuttle's first flight could be its last. It was crewed by 2 men, Commander John Young, NASA's most experienced astronaut, and first-time space flyer Bob Crippen. On April 12, 1981, the world held its breath for the maiden voyage of Space Shuttle Columbia. This was to be the first time a new launch vehicle had been tested with men on board.
Toward the White Room, in which they will be prepared for entry into the orbiter. T-minus 10, 9, 8, 7, 6, 5, 4. We've gone for main engine start. We have main engine start. Liftoff from America's first space shuttle. And the shuttle has cleared the tower.
Speeding into space, Columbia carried the hopes for the space program. The shuttle was to prove so successful that even America's biggest rival in space decided to copy it. This is the Soviet shuttle. Its name is Buran, meaning blizzard. Buran was developed in the early 1980s to give the USSR its own spaceplane. It contained design concepts almost identical to NASA's shuttle. Its designers later admitted borrowing the American blueprints. Buran was designed to be launched simply as a payload. It's strapped to the side of the world's most powerful rocket, the giant Energie. In 1988, Buran made its first and only flight. After completing this faultless test flight in 3 hours, Buran touched down to the cheers of the Soviet Space Administration. Unmanned, Buran had orbited twice around the world. Its whole mission had been entirely controlled by computers. With the breakup of the Soviet Union and a cash-strapped Russian economy, the project has been shelved. Once the pride of its space program, Russia's spaceplane Buran is going nowhere. But it had proved that computers, as well as astronauts, can command the world's future spaceplanes.
When I first started flying, it was sticks and cables and pulleys and things, and then you get to this thing and you're totally dependent upon the computers, and so you just have to put your trust and confidence in them. You have to. You have no choice. I mean, everything depends on those computers.
Launch day, and another flight of NASA's spaceplane is about to begin. As the liftoff approaches, 3 miles away in a reinforced bunker called the firing room, more than 300 engineers and technicians are preparing themselves for the most critical moment of the mission.
The orbiter is literally loaded with liquid oxygen and hydrogen potential explosions, and it's an extremely dynamic situation for us. There are hundreds and hundreds of things that must be monitored, hundreds of things that could go wrong. We have to know extensive information about each and every system on board.
With 20 seconds remaining to liftoff, the launch becomes too complex for humans to handle.
T-minus 15 seconds. 12, 11, 10, 9, 8. We have a go for engine start. 3.
As it fires its main engines, deep in the bowels of the world's most complex machine, the shuttle's computers make over 4 million decisions every second. The destiny of the crew is totally dependent on whether those decisions are right or wrong.
Booster ignition and liftoff of Endeavour in pursuit of a Japanese satellite.
Roger, roll, Endeavour.
The shuttle is designed to operate at the very limits of performance. Without its computers, this highly unstable spaceplane would lose control in seconds and crash. Computers must fly it from launch to landing with absolute precision. Although well over 20 years old, the shuttle's computer systems are even now unequaled in complexity and reliability. Each orbiter carries 5 identical computers. They're responsible for the simultaneous control of millions of components.
One of the most remarkable things about the shuttle is that in addition to monitoring all of the systems on board the shuttle for normal operation, simultaneously it has to consider literally an infinite number of scenarios that might occur in the face of failures or unexpected events, and take the right action with split-second accuracy for every one of those situations. It has to do it right every time because you don't get a second chance.
During every moment of the orbiter's journey, over 10 million sensors and instruments located throughout its structure are feeding its computers vital flight information along 2,000 miles of wires. Ruthlessly searching for errors, any problems they detect are dealt with in a most unusual fashion. Like an electronic jury, its computers discuss the problem, then vote for the best solution. The computers collaborate and solve life-threatening problems before the crew even know they exist.
25.
Standing by to activate the sound suppression water system.
15.
T-minus 10, 9, 8, 7. Go for main engine start. 3 main engines up and burning. 3. We have a cutoff.
In over 80 flights, there have been only 5 aborted launches, where the computers shut off the main engines with less than 3 seconds to lift off.
No MPS fire detectors tripped.
Orbiter access arm now back in position. Discovery is now in the safe configuration. Crew is in no danger.
The computers have worked perfectly every time.
MPS copies
Successful space exploration depends upon an obsession with safety.
There is no error that's acceptable. There's no room for error. There's no opportunity for failure that we can allow with the software on shuttle missions. Human lives depend on it.
The hands those lives depend on are those of more than 300 specialist programmers who spend 3 years creating instructions unique to each mission. Symbol by symbol, character by character, these programmers write more than 420,000 lines of numbers and letters that will control the shuttle during every second of its mission. They are creating an electronic brain. With the lives of the crew at stake, there is no room for error. To make sure it's foolproof, the code is put through the most rigorous testing process in the world. Creating every problem imaginable, the entire mission is rehearsed by the computers more than 10 times before it even takes place.
We have a go for engine start. 5, 4, 3, 2. Booster ignition and liftoff.
But once the computers have ignited the solid rocket boosters, there's no turning back. No other machine on Earth possesses quite so much muscle. In order to lift off, the space shuttle uses 2 systems of propulsion, its twin solid rocket boosters and 3 liquid rocket engines located in the orbiter. Designed to last for 55 flights, the 3 main engines built into the orbiter are the only reusable liquid rockets ever built. Compact and lightweight, they are the most powerful and sophisticated rocket engines of their size.
Pound for pound, these engines are extremely powerful. Of course, they need to be powerful if you're going to kick an orbiter into low Earth orbit in 8.5 minutes.
Fueled by a mixture of liquid hydrogen and liquid oxygen, each engine develops over 12 million horsepower, more power than 64,000 V8 car engines. To achieve this power, they must operate at extremes of temperature and pressure.
When we ignite this engine, what you're seeing is probably one of the most dramatic cold starts of any engine in the world.
Prior to ignition, this engine is literally frozen by liquid hydrogen. As the engine fires, its temperature instantly jumps from below 0 to 6,000 degrees, and it reaches full power in just 1,000th of a second. But these rockets provide only 1/4 of the shuttle's total thrust. Just feet away from the astronaut's cabin are the most powerful rockets in the world, the solid rocket boosters. Standing as high as the Washington Monument, they are loaded with 500 tons of dry rocket fuel. In less than 2 minutes, they rocket the shuttle to an altitude of 30 miles at 9 times the speed of sound. But the amazing power of solid rockets has one disadvantage. Once started, they can't be stopped, as the crew of Challenger discovered on January 28, 1986.
21 seconds. Solid rocket.
It was the worst accident in NASA's history.
9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
3 good APUs.
velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles. Engines throttling up. 3 engines now at 104%.
Challenger, go at throttle up.
Challenger, go at throttle up. Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
Man's finest machine had failed. But how?
Flight GC, we've had negative contact, lost downlink.
Soon after liftoff, the right solid rocket booster developed a serious leak of red-hot gases from its lower joint. A bright flame can be seen licking the side of its external tank. As the flight continued, the gases burned away the booster's lower strut, eventually causing it to tilt into and puncture the external tank. 500,000 gallons of hydrogen ignited in a giant fireball. But it wasn't the explosion that killed the Challenger crew. The tiny compartment containing the crew remained intact, clearly visible as it plummeted to the ocean beneath. Many experts believe that inside, some of the crew were still conscious until the fatal impact with the water, over 2 minutes later. NASA recovered slowly from the tragedy. After taking the remaining fleet out of service for 2 years, it redesigned the solid boosters and developed new escape systems and safety drills. In more than 50 missions since Challenger's tragic loss, there have been no further problems. But man's most amazing machine still has one major problem. It's getting old and out of date.
The Shuttle is a beautiful machine. It does everything we ask it to do, but it was designed in the 70s and has old technology and is very expensive. It's got an external tank that we throw away every time. It's got solid rocket motors that need to be refurbed every time. It takes a lot of people, a lot of infrastructure to go do that.
As we move toward the year 2000, our current generation of space planes faces a serious problem. They consume huge amounts of money. They are pricing themselves out of business. Maintaining NASA's fleet of 4 shuttles requires the full-time attention of nearly 30,000 people. It costs several $100 million to send each astronaut into space. The cost of just one launch has been estimated at $1 billion. So the race is on to design and build a far more cost-effective launch system. The need to have a fleet of commercial spaceplanes is greater than ever before. As we consume and demand more and more information, faster and cheaper spaceplanes are needed to deliver thousands of satellites into orbit. A new breed of spaceplane is already on the way. The Japanese space agency, NASDA, is developing a small spaceplane called HOPE. Designed to ferry astronauts and cargo to the International Space Station, HOPE could be in operation early next century. The French have a different concept. Named Hermes, their spaceplane is designed to be launched on top of an Ariane 5 rocket. Carrying up to 4 tons in payload, Hermes will carry astronauts and materials to and from the International Space Station. The future is within our grasp.
What we're trying to do is take advantage of technology and have a vehicle that flies more like an airplane. that you take off and land. You don't have to throw things away. You don't have to refurb it as much. It takes advantage of things that we've learned for the last 25 years. If we do that, we can have greater access to space, explore the universe, and do some really great science.
In the foreseeable future, space planes will be a part of everyday life. But what will their destinations be? Some will literally be superfast transporters to other countries. Traveling at a height of 70 miles, spaceplane passengers will fly from New York to Tokyo in 30 minutes. Others will dock at the International Space Station, already under construction. As fleets of spaceplanes bring equipment and materials from Earth, we will build new space stations for future travelers. Ordinary citizens will travel to luxury hotels and orbiting universities. When the problems of prolonged weightlessness on the human body have been solved, a new breed of spacefarers will commute daily into orbit. A later generation of spaceplanes will even allow us to voyage to manned bases on the moon. And one day, spaceplanes will provide the springboard for deep space exploration.
On some planets, storms are impossible. Superheated Mercury is too small and too close to our sun to have a significant atmosphere. And no atmosphere means no storms. But move out away from the sun, and we find worlds with turbulent, chaotic atmospheres. They can spawn some of the most awe-inspiring megastorms in our solar system. This is Venus, a planet completely shrouded with clouds. Winds rip around the upper atmosphere at over 300 miles per hour.
About 35 miles above the surface, the winds are whipping around in a ferocious pattern that basically carries the cloud features around the entire planet every 4 days.
Venus is closer to the sun than Earth, and it's heat from the sun that drives the wind.
The circulation pattern of Venus's clouds is actually quite simple. There's a warm side of Venus and a cold side. And as air warms up and rises on the day side of Venus, it spreads around to the night side. So there's this continuous current. It's actually quite a lot simpler than the atmospheric circulation on Earth.
Venus's winds circulate faster than the fastest hurricane on Earth. But they look very similar. The Venus Express probe captured these remarkable images of the planet's south pole.
One of the great mysteries of Venus, which actually had jaws dropping in the halls of many astronomy departments, is the fact that we have hurricanes at the poles of Venus, especially in the southern hemisphere, that have two eyes. Not one eye, but two eyes. Now, we've never seen this before on such a planetary scale.
Venus's double-eyed vortex is 1,800 miles wide. Two hurricanes whirl around each other.
If you could descend into the vortex of Venus, something I would love to do, at least with a remote machine, I think you would see some kind of a fantastic wall of cloud and this sort of twisting form spinning around you at ferocious speeds. It would be quite a sight.
It's a mystery how deep this raging, spinning vortex goes. But maybe this megastorm eye descends to the planet's surface. Down here, permanent twilight bathes a volcanic landscape, and the atmosphere's colossal weight creates immense pressure.
And the atmospheric pressure on Venus is about 100 times that of the Earth. Think of taking a car, squeezing it down to about a square inch and putting it on every square inch of your skin. You'd be flattened within a fraction of a second because of all that pressure.
Venus's dense atmosphere creates one of the strangest megastorms imaginable. 4 miles per hour winds with the force of a hurricane.
The winds on the surface of Venus are actually very slow because Venus has a very slow rotation rate. It takes Venus about 8 months to turn once around with respect to the sun.
The crushing atmospheric pressure rams gas molecules together so tightly that they feel more like a liquid. A gentle 4-mile-an-hour breeze packs a brutal punch. It's like a hurricane in slow motion.
Winds on Venus are totally unlike anything we see on the planet Earth. You would almost feel like a molasses effect. It'd be quite difficult to simply walk and run right through the wind.
Venus's surface is so hostile that life is impossible here. But the upper atmosphere's faster winds hold an extraordinary possibility.
Well, I harbor this, I don't know if I would call it a hypothesis or a scientific fantasy, but I do think it's plausible that there could be some kind of life living in the clouds of Venus. There are certainly energy sources, there's sunlight, and there are certainly nutrients. There's carbon, there's hydrogen, there's oxygen. All the stuff we think of that you need to make life exists in the clouds of Venus.
Earth's upper atmosphere is full of life. Microscopic bacteria drifting on the wind. Could Venus be the same? Perhaps one day we'll send a probe to find out. Leave Venus behind, and the next planet is Earth. Here, too, the weather gets extreme. We are bombarded by tornadoes, hurricanes, and these dust storms. On Earth, they're localized. But on the next planet out, they engulf an entire world. Over 100 years ago, astronomers thought they had found life on Mars. A dark wave spread from the pole towards the equator. They thought it was springtime vegetation spreading across the planet. They were right about the season.
Mars tilts at roughly 23 degrees like the Earth, so you would have summer, fall, winter, spring like the seasons.
Seasons bring weather. The shadow astronomers saw was actually dark rock uncovered by a violent dust storm. It's all because of the way the planet tilts. The Earth takes 1 year to orbit the Sun. In January, the northern hemisphere leans away from the Sun, and we get our winter. In June, it leans inwards, our summer.
Mars has gigantic planetary dust storms, the like of which we've never seen here on the planet Earth.
Mars has around the same tilt as Earth, and springtime means storms. The Martian surface vanishes under a cloud of raging dust particles. On Earth, we get dust storms too. They can be devastating, swallowing entire cities. July 5th, 2011, Arizona. An unstoppable 5,000-foot-high wall of dust smashes into Phoenix. Day turns to night. Thousands of tons of dust settle over the city. But the disaster stays in one place. Mars's dust storms can engulf the entire planet.
On Mars, when dust gets kicked up once, it lands, it can get kicked up again and again. The dust is reusable. On the Earth, when dust gets kicked up and then finally settles out, it's probably going to settle out into the ocean, where it's gone for good.
There's nowhere on Mars where there isn't ready dust and sand to add to that storm. So these storm systems can kick up and last weeks or even months.
Mars's incredibly dry atmosphere contributes to the storm's size and power.
In the case of the Earth, dust that gets up into the atmosphere is rapidly washed out by the rain and gets into the ocean. In the case of Mars, there's no comparable rain to wash the dust out. So once the dust gets into the atmosphere, it just sits there until the particles by themselves are able to slowly settle out.
A lack of rain allows Mars's dust storms to cover the planet. But dust storms on Mars can be equally spectacular on a much smaller scale. NASA rovers captured these extraordinary images. Dust devils sucking up fine, dry iron oxide dust. The biggest dust devils can reach 6 miles into the sky. They pump fine particles high into Mars's atmosphere, creating a haze of dust that may help control the planet's dry climate and lead to a planet-wide megastorm. Even on Mars, dust storms this big are rare. Astronomers have detected just 10 in the last 100 years. What the ancient astronomers mistook for life was a megastorm. But even a planet-covering dust storm is dwarfed by the weather on the next planet out from our sun. This is the giant of our solar system, Jupiter. Jupiter is gigantic. It's 2.5 times more massive than all the other planets in the solar system added together. It's also home to gigantic megastorms. Jupiter's high-speed rotation drives vast bands of counter-rotating clouds. Colossal storms build along the boundaries. And this is the biggest of them all. The oldest storm in the solar system. 15,000 miles across and over 300 years old. The Great Red Spot. Around the edges, turbulent winds rage at over 300 miles per hour.
The Great Red Spot is a giant vortex, meaning that in the case of the red spot, it has a high pressure center with winds that swirl around the outer edge. So in that sense, the Great Red Spot is a little bit like a hurricane.
A hurricane with a difference. On Earth, hurricanes feed off heat from the ocean. When they hit land, they start to die. So on average, they last only about a week.
Jupiter does not have land. Jupiter is a completely gaseous planet, and the friction there is very weak. And so a vortex, like the Great Red Spot, can last indefinitely. There's nothing to slow it down.
To keep going, all the red spot needs is a power source. On Earth, ultimately that's heat from the sun. But Jupiter's 5 times farther from the sun than us. Heat from the sun is not enough to drive the red spot. Instead, Jupiter has an internal power source, its own immense gravity. In 1995, NASA launched a probe straight toward the giant planet's heart. It plunged into Jupiter's upper atmosphere at over 106,000 miles per hour. As it fell, the planet's crushing gravity ratcheted up the pressure 10, 15, 20 times what we feel on Earth. Winds gusted to over 400 miles per hour. The probe gave out just 100 miles in, crushed by pressure and fried by the incredible heat the pressure generated. Had the probe made it deeper, it would have reached a vast silvery ocean. Intense pressures here turn hydrogen gas into a churning metallic liquid, superheated to over 40,000 degrees Fahrenheit. Jupiter's interior pumps out about twice as much energy as the surface gets from the sun. This is Jupiter's power source, the heat that drives its massive megastorms.
All of the convection, all of the heat comes from the hot, dense interior of the planet itself. So the bands of clouds that you see that are even counter-rotating, going in different directions, those are all driven by the internal heat of Jupiter itself.
Jupiter's internal heat drives its violent megastorms. But the giant planet may hold clues to an even deeper mystery. Could life exist on other worlds? NASA's Cassini probe studied Jupiter as it flew past en route to Saturn. It made an extraordinary discovery. Strange white clouds just north of the Great Red Spot. Clouds just like the clouds on Earth. Droplets of liquid water. Could Jupiter have the ingredients for life?
The question of life on the giant planets is an interesting one. You have many of the ingredients for life. You have sunlight coming in, there's liquid water, at least in the form of cloud droplets. On the other hand, if life can easily exist in clouds, you might expect that bacteria and algae would populate the clouds on Earth and the clouds would be green. We don't see that on the Earth. We do see microbes at many altitudes throughout the Earth's atmosphere, but they seem to largely be blown off of the surface.
It's likely that life on Earth began on a solid surface. But could life evolve without one?
There's no surface on Jupiter, and so that makes it difficult for organisms to have a constant source of water. So if you imagine yourself being a little bacterium inside a cloud droplet, you're going to be in deep trouble when that cloud droplet evaporates.
Whether life exists in Jupiter's clouds or not, gas giants like Jupiter and its neighbor Saturn have all the right ingredients: water, heat, and one other vital element: a spark. Lightning on an unimaginable scale. These haunting images are from NASA's Cassini probe. Its mission: to explore one of the solar system's most awe-inspiring planets, Saturn. The probe reveals Saturn's rings, moons, and the planet itself in near-perfect detail. Chaotic bands of cloud race around Saturn at more than 1,000 miles per hour. Finding storms here was no surprise. It's a planet of storms. But this was astonishing. A bolt of lightning. A gigantic thunderstorm on an alien world. Lightning creates some of the most spectacular weather on Earth. Electrical tension builds between the top and bottom of a vast 55,000 feet high storm cloud. A maelstrom of water vapor, rain, and ice. Tiny ice crystals drive up past hailstones falling down. As they rub past each other, it builds up a charge. When the strain gets too great, you get an electric spark. On Earth, the average lightning storm stretches 15 miles. On Saturn, they can reach around the whole planet.
There are examples of lightning storms on Jupiter and Saturn where the anvil cloud, in other words, the big cloud at the top of the storm, starts small and grows to be 20,000 kilometers long. That's the size of the Earth.
On Saturn, we registered one lightning storm that was 10,000 times greater than any lightning storm found on the planet Earth.
Lightning is hotter than the surface of the sun. The atmosphere literally explodes. The sound we call thunder. On Earth, it's the sound of new life.
Lightning seems scary and destructive, but actually it's very productive for life on Earth. And the reason why is because of its influence on atmospheric chemistry.
Every bolt literally burns the air.
When you have a lightning discharge, you get this very high temperature, very energetic plasma, and that breaks up the nitrogen molecules in the atmosphere, frees up those nitrogen atoms to enter into other kinds of molecules, and those nitrates formed by lightning allow nitrogen to go into the soil as basically fertilizer, enter into plants, enter into the life cycle. So it's the lightning that frees up nitrogen atoms in the service of life on Earth.
Earth experiences 8 million lightning bolts every day, helping life evolve and colonize the planet. But for Saturn, lightning alone may not be enough. There's nowhere for alien life to live. One place in our solar system may solve that problem. Saturn's moon, Titan. It has an atmosphere. It has lakes of liquid methane. And its own bizarre brand of megastorm. Saturn is almost 900 million miles from the Sun. This far out, orbiting the Sun takes time. Saturn's year is nearly 30 Earth years long. Right now it's spring, and things are heating up.
Moving into the summer cycle of Saturn. So the atmosphere is slightly heating up, even as distant as Saturn is from the Sun. We've got a little more energy, and we're seeing the most spectacular storms we've ever observed on Saturn.
After years of frozen silence, Saturn is coming alive. Scientists have waited nearly 15 years for the Sun to light up its North Pole, to reveal extraordinary details about one of the strangest megastorms in the solar system. Saturn's unique hexagon storm.
A hexagonal pattern, how can that be? In Mother Nature, we have jagged objects. We don't have geometric figures arranged precisely, especially at a gigantic planetary scale. However, there's some theories. If I take a bucket of water or a bathtub and simply vibrate it, I get waves, waves that travel. But there's another kind of wave. You have traveling waves, but then you have stationary waves. Inside a bucket of water, you can get resonances. Water pulsates like this. And you can also get them to pulsate in a circle like this to create regular patterns. These are called stationary waves, and we think that this mysterious hexagonal pattern on Saturn is a hexagonal standing wave.
The megastorm at Saturn's North Pole is a wind that travels at hurricane speed, cornering sharply 6 times as it races round the planet. The central clearing is so big, you could fit 4 Earths inside. What lies beneath its surface is a mystery. As Saturn warms from spring to summer, another world comes alive too. One of Saturn's moons, Titan, is warming up. And with the warmth come the storms.
One of the most interesting moons in our solar system is Titan. It's straight out of science fiction. It's an object with yellow skies and methane clouds that is truly remarkable.
NASA's Cassini probe reveals Titan in unprecedented detail. A thick, dense atmosphere, vast mountain ranges, lakes of liquid methane. And this, an arrow-shaped band of white methane clouds moving over its surface. When the clouds drifted over a dusty open plain, seen here as a dark patch, the dark patch of ground beneath the clouds grew larger. Scientists believe liquid methane drenched the surface. A spring rain storm, Titan style.
Rain on Titan, if it exists, would be very different from rain on the planet Earth. First of all, the gravitational field is very weak, so you would actually see raindrops falling very slowly at you. Also, the size of these droplets could be much larger. But don't get caught in a rainstorm on Titan. Those droplets are awfully cold.
Titan's methane monsoon sweeps across the moon. Weak gravity creates ultra-cold, hazelnut-sized raindrops, an alien world with truly alien weather. These slow drops have carved valleys and lakes, much like ours on Earth. A slow-motion megastorm. But fly even farther out through the solar system, and you find storms that are altogether faster. This is super-chilled Neptune. The temperature never gets above 300 degrees below zero.
Neptune is one of these giant planets. It's much larger than the Earth and has a very thick atmosphere. It's about 2 billion miles out from the sun. So you really might expect, since it's that far from the sun, it would be very cold and not have very much weather. But in fact, Neptune is very dynamic. It's got tremendous weather patterns.
Despite its incredible distance from Earth, astronomers can get close to Neptune's turbulent atmosphere. With a little help from this. The Keck Observatory. 14,000 feet up on the summit of Mauna Kea in Hawaii. It sits above Earth's clouds and pollution. The telescopes are so powerful, they could see a candle on the moon. Neptune at first appears featureless, but a closer look reveals white, high-altitude clouds in the upper atmosphere. It's a perfect opportunity to track wind speed. Measuring the time and distance the clouds take between 2 points allows scientists to clock their speed. The Keck telescope swings towards Neptune. A series of shots track the white clouds as they move around the planet.
So here we can take several photographs that show the positions of clouds apparently changing. You can measure the position at one moment to be there, and at another time, a few hours later, to be in a different place. Now, most of that change in position is due to the rotation of the planet as a whole. However, if you know the rotation rate and subtract that out, that gives you the motion of the clouds relative to the planet. That tells you the wind speed.
The results are shocking.
We're seeing wind speeds on Neptune of many hundreds of miles per hour, up to 12 or even 1,260 miles per hour for the very fastest clouds. That's really phenomenal.
Neptune has the fastest winds in the solar system.
So what's driving this? You need energy to make weather. Where's that energy coming from? And it turns out it's coming from Neptune itself. It does receive sunlight, but Neptune actually radiates away more energy, a lot more energy than it gets from the sun, which means the interior is very hot. Probably it means there's radioactive material in there, there's leftover heat from when Neptune formed 4.5 billion years ago that's very slowly leaking out. And it's that that's heating up the air and driving all of the circulation and all of this crazy weather that Neptune has.
Neptune's storms hit hard. But the search for truly extreme weather takes us out of the solar system altogether, into uncharted territory. Out here, there are storms that make even Neptune's winds look like a breeze.
Katrina was just a sneeze compared to the winds we have on Osiris.
The search for megastorms leads to alien worlds whose violence defies imagination. Space is full of stars and planets where violence and chaos reign. Astronomers scour the skies for new worlds, and the king of the planet hunters is Professor Jeff Marcy. He scans the night sky seeking new worlds around distant stars. Marcy's team has instruments so sensitive they can even predict the weather on these distant planets. This is Osiris, 150 light years from Earth. A planet from hell with matching weather. Earth is 93 million miles from the sun. It orbits the sun in 1 year. But Osiris is just 4 million miles from its star. Its year races by in just 3.5 days. When Osiris passes between us and its star, starlight briefly shines through its atmosphere, giving us a glimpse of conditions on the alien world.
And they waited until the planet was in front of the star. At that moment, some of the starlight passed through the atmosphere of the planet. They were able to do essentially a chemical assay, a chemical assessment of the composition of this atmosphere.
Osiris gets blasted by the intense heat of its star. Temperatures top 2,000 degrees.
Now, what that means is that the environment on that planet is, well, hideous for life as we know it. But even more, the intense heat causes the gases to expand, and they have no place to go but the backside of the planet.
Osiris is tidally locked. The same side of the planet always faces the star. The other looks out into space. The temperature difference is immense. Superheated atmosphere roars from the bright side of the planet to the dark at nearly 6 times the speed of sound.
In fact, the winds will be something like 2,000 or 3,000 miles per hour. Enormous speeds of these winds, 10 times, 20 times faster wind speeds than the strongest hurricanes. Katrina was just a sneeze compared to the winds we have on Osiris.
Osiris is a brutal world. Too hot and too violent for any kind of life we could imagine. But there are even larger megastorms, storms on the scale of whole galaxies. And these vast storms may be the reason any of us are here. The Hubble Space Telescope captured this stunning image of the galaxy NGC 3079. At its center, a superwind, a storm on a truly cosmic scale. It was triggered by an explosion from a forming star. This raging galactic storm is about 3,000 light years wide. It has already raged for around 1 million years. Filaments of 20 million degree gas tower above the spiral galaxy. This cosmic megastorm wreaks havoc within its host galaxy.
We see bubbles and jets and formations of gas falling into the galaxy, colliding with galactic dust.
The gas from the galactic megastorm smashes into gas and dust at the heart of the galaxy and compresses it into a swirling mass of matter. Gravity takes over. The compressed clouds of gas and dust get tighter and tighter. The center gets hotter and hotter. Finally, it ignites. Powerful winds from the new star blast into space. The whole cycle begins over again, and a new galactic megastorm is born. Around the fledgling stars, dust and rock come together. The birth of new worlds with rocky surfaces where life could begin.
And perhaps the formation of life itself may be determined by how these gases swirl and create supergalactic storms. And if you have galactic winds churning away, then that would help to distribute the elements necessary for life throughout the galaxy. So galactic storms may in some sense be one clue to the formation of life itself.
Galactic megastorms rage for millions of years. Billions of years ago, they may have created new homes for life in our Milky Way galaxy. On every scale, storms are not just a force of destruction. They are linked to creation itself. The search for life on other worlds is also the search for storms.
When you disrupt the status quo, you open all kinds of possibilities for things to reassemble in different ways. So chaos or disruption is actually an important factor in the development of complex systems like life.
A planet that might have changes of seasons, volcanism, intense storms, some environmental factors that you might think could be damaging to life, in the long run makes life stronger.
A dramatic streak of light across the sky, a passing comet, is an astonishing sight.
They're beautiful, these fuzzy glowing balls with the tail coming off. It's really something. You just don't get to see an object like that very often.
Comets are extraordinary. If you get to see a comet for the very first time, it'll stick with you forever.
The journey of a comet as it sails through the solar system is the most fantastic of all astronomical objects.
It loops in toward the sun from the depths of space, an odyssey that can last millions of years. Many pass by the Earth so often, they're almost like old friends. Every comet is a frozen mass of rock and ice several miles across. But all we see is a glowing ball of light and a long, sweeping tail. Yet comets are more than cosmic fireworks. They could help unlock some of the deepest mysteries in science.
We're trying to figure out as scientists where we came from, and that means everything from the beginning of the universe to the beginning of the solar system to how life started. Comets really fit into that. They really give us clues about how the solar system formed. If we can't understand comets, we don't understand how we got here.
Comets may even be the source of life itself.
We may owe our existence to the fact that comets billions of years ago came to Earth and brought the necessary ingredients for life.
They can also cause enormous destruction. comets could kill us all.
If a comet were to hit the Earth, watch out. It would be a planet buster. It would be an object sufficient to wipe out all life as we know it on the planet.
Learn about comets, and just maybe we will learn how to survive them and begin to understand how the universe works.
When we study them, we're learning what the solar system was like when it was first forming, and we can learn about what other solar systems were like as well. And hopefully that will teach us a tremendous amount about how stars form and how planets form, and how comets themselves were originally formed.
Comets date back to the birth of our solar system 4.5 billion years ago. They were made by the same force that created the solar system, gravity. It began in a maelstrom of chaos. A giant cloud of gas and dust collapsed to form a whirling disk. Close to the sun, it was burning hot. But further out, it was cool enough for gas clouds to condense and freeze. Ice crystals fused with grains of dust. They slowly pulled together into larger and larger masses.
Over time, these sort of snowballed, like a snowball rolling downhill, picking up more and more and more material.
Eventually, they formed gas giants like Jupiter and Saturn. But not all the debris in the disk turned into planets. Trillions of lumps of dirty ice were left behind. The comets.
You could almost think of comets as sort of the frozen leftovers of the formation of the solar system.
They are almost unchanged to this day.
They're pristine time capsules, and if you could crack one open and see what was inside, you could literally see what the solar system was first made out of. That's remarkable.
But the comets did not stay put. Several 100 million years later, the solar system plunged into turmoil once again. Encounters with debris pulled the gas giants out of position. The giants' immense gravity then hurled comets in every direction, flinging trillions of tons of material from the dawn of the solar system into the cold outer reaches of space. Some comets settled in a region 4,000 million miles from the sun, the Kuiper Belt. But most were tossed even farther out to form a giant sphere around the entire solar system. We call it the Oort cloud.
This is a region of our solar system that's farthest away from the sun. The sun is just a tiny little dot, one of many stars. And the whole area of space around you is virtually empty. There's nothing there, very little. And just occasionally you'll find the odd comet floating out there in deep freeze, cold, dark, and very much alone.
In this remote ice cloud, there are more than 1 trillion comets. They can take millions of years to orbit the sun. But they don't always stay here. The orbit of every comet is a delicate gravitational balance. The smallest nudge can tip the scale.
Most comets spend their entire lifespan billions of miles from the sun, motionless, inert, simply waiting for something to happen. But then, perhaps a random collision takes place. Perhaps a passing star nudges it, and then the gravitational force of the sun inevitably pulls it toward the inner solar system.
Gravity, the force that created the comets, then flung them to the edge of the solar system, now pulls them back in. Our comet begins its epic odyssey to spread life or death across the solar system. More than 1 trillion comets circle the sun at the frozen edges of our solar system. But many do not stay here. The smallest gravitational disruption can knock them out of their orbit.
It could be a nearby star going by. It could be us going through a denser part of the galaxy. Anything that just gives a little gravitational hit to a comet can cause it to fall in towards us.
Our comet has been disturbed. Now the sun's immense gravity takes over.
You can think of the gravity of our solar system sort of like being a hillside. At the bottom, there's the sun, and comets are way at the top of that hill. When they get dislodged, there's only one way for them to go. They have to fall down in towards the sun.
Our comet accelerates towards the sun, but its path is far from straight. Gravity from the planets can throw comets off course or out of the solar system completely. If they escape these obstacles, comets continue their journey toward the sun. Now they begin one of the most remarkable transformations known to science.
A chrysalis to a butterfly. They become the most spectacular things the universe has to offer.
As it passes Jupiter, our comet begins to change.
As it starts to move a little bit faster and starts getting closer and closer to the sun, and it starts feeling the heat of the sun, that's when things really start to change.
"500 million miles from the sun, heat brings our comet to life. Frozen gases start to vaporize. Grains of ice and dust rise from the surface.
As the comet continues to approach the sun and gets warmer, more and more gas is released. The comet becomes a fuzzy ball. There's a solid part in there, but it's surrounded by a much larger sort of cloud of material.
This cloud of dust and gas forms an atmosphere or coma around the comet. And it also creates the comet's huge tail. It's all driven by the sun, and it's not over yet.
There's something called the solar wind. It's actually a huge wave of charged particles originating from the sun. This fills our solar system, and as a comet begins to move further and further in towards the sun, the solar wind gets stronger.
Like a cosmic hurricane, the solar wind blasts gas molecules from our comet out into space. They form a second giant tail.
The solid part of the comet might only be a few miles across, and the fuzzy part might be a few thousand or tens of thousands of miles across. The tail that gets swept back as that material is blown off by the solar wind can be millions or tens of millions of miles long.
Our comet hurtles through space at 50,000 miles an hour. It's about to enter the most violent phase of its journey. 200 million miles from the sun, water ice begins to vaporize.
The ground would start to shift and quake, and as the material beneath my feet is literally thawing, we'd have great big jets of carbon dioxide and water ice starting to come out, and that would not be a very good place to be standing.
The surface cracks open. Gases explode. Debris fires in all directions. The force of these eruptions makes the comet tumble erratically.
Every jet that turns on is literally like a little jet engine attached to the comet.
Like a dragster on a racetrack, our comet explodes to life. Incredible speed, irresistible energy, and a vast plume of debris. Our comet transforms into a cosmic hot rod, but speed and energy are a volatile mix. our comet could blow apart at any moment. The cloud around our comet is now bigger than Jupiter. Its tail stretches for 100 million miles. An object 4.5 billion years old emerges from the dark.
Every arrival of a new comet is like a gift from the universe. We've never seen this little bit of the solar system before. This little building block, this little baby picture, it's completely new to us.
It's a chance to study the origin of our solar system. And what we're learning is a revelation. Comets are far more hostile and alien than we imagined. With modern telescopes, we can study comets in more detail than ever before. But to really understand them, we need to get close to the very heart of a comet, its nucleus.
One of the holy grails of comet science is to really understand what is in a comet's nucleus, what is actually on the surface, what is the chemical composition, what are the characteristics of the rocks and the materials, the volatiles that are on that surface.
The nucleus is the fundamental building block of the solar system that we as scientists really want to investigate. That's where the mysteries really are.
There have been more than a dozen missions to comets in the past 3 decades. Every one of them has been a revelation.
We've learned about the chemistry of them. We've learned about the physical interaction they have with the sun. We've learned about their physical surface, their terrain, and how they're different even if you were to go from one spot on a comet to another. So we're really learning that these things are worlds unto themselves.
Scientists thought comets were white, like a snowball. That changed in 1986. When the Giotto space probe beamed back these images of Halley's Comet.
For the first time in history, we had a snapshot of the very center of that comet that entered human history on many occasions, and we found a cold, dead world. We found an object shaped like a peanut.
Halley was no snowball. A thick layer of black dust covered its surface. There were pits and hills, and Halley was 9 miles long, far bigger than anyone expected. Scientists thought that all comets were the same. They were wrong. In 2004, the Stardust probe flew into the tail of Comet Wild 2 and captured thousands of tiny dust particles.
When Stardust brought those samples back on Earth, we realized that, in fact, every comet is a unique object. Just like every planet is different, it looks like every comet is different. It has its own history to tell. Different materials went into its formation, different heat sources were injected into its interior, different chemical processes and geologic processes occurred. Each one is a unique world waiting to be explored.
Some comets are truly strange. These are real images of Hartley 2, a comet so weird, it snows.
It's so strange. We were able to see that there are golf ball-sized chunks of dry ice that are following the comet around up to 1 million miles away from the nucleus. This thing is just making a big mess.
Hartley 2 is just amazing. It looked like you were in the middle of a snow globe and you shook it up and there are all these little things, kind of like flies buzzing around food, just kind of floating out there. It's just not right.
Hartley 2 is a hyperactive comet. It tumbles faster and spits out more debris than most others its size. Comets are alien worlds. On Comet Tempel 1, there are smooth plateaus, craters and cliffs 60 feet high. Layers of rock lie on top of each other like a stack of pancakes. Each comet seems to have its own unique history. Tempel 1 gave scientists their biggest breakthrough. In 2005, the Deep Impact Space Probe slammed a projectile into its surface. The explosion dug out a crater 150 yards across.
Talk about a spectacular 4th of July. I mean, can you imagine anything better? We actually blew a hole in a comet. I mean, that's got to be one of the more amazing things that NASA has ever done.
The material the impact ejected allowed us to see inside a comet's nucleus for the first time.
It was completely unexpected. We found things like rubies and peridot, gemstones, tiny little things inside the comet. And we found all kinds of organic molecules, the very sorts of things we're made of.
Scientists now believe that comets play a critical role in our universe.
Where do the ingredients of life come from? Where were they all mixed together? Where did all this liquid water come from? Comets could hold the key to understanding the nature of life itself.
But opportunities to study them up close are rare. Our comet is now moving at incredible speed toward a place where no spacecraft could ever survive: the Sun. 4 billion years ago, gravity hurled comets to the edges of our solar system. The same force can pull them back in. Our comet passes Earth and enters the most violent stage of its journey. It rockets toward the Sun at 100,000 miles per hour.
The surface of the comet is now sizzling with activity. Blistering temperatures are being created. Enormous geysers of ice crystals and gas being shot off the surface.
Jets are erupting all over the place. It's tumbling, the rotational state is changing, and the very surface is kind of cracking up underneath our feet.
Inside the comet, pockets of gas explode and fling huge rocks into space.
It's losing mass, it's shrinking. And as we get closer and closer to the sun and more of the volatiles are starting to come off of its surface, this can actually change the rotational state of the comet. It can make it tumble, it can actually even push it in its orbit. It can actually change the orbit of the comet.
Comets can shed 50 tons of ice and gas every second. Enormous pressures build up inside the nucleus.
It could become unstable. It could even break apart into pieces at any time.
As comets reach their closest point to the sun, their existence is on a knife edge. Many will not survive.
We've been able to actually see images of comets just getting swallowed up by the sun. And you can actually see them just pelting in there, and the whole body, whether it's a mile across or 10 miles across, just gets completely and utterly destroyed.
A solar observatory recorded these extraordinary images. They show small comets called sun grazers diving towards the sun. Here they're exposed to immense gravity and torched by the ferocious heat of the sun. Many are vaporized. Even in deep space, vast explosions can tear comets apart. In 2007, Comet Holmes was heading away from the sun when something extraordinary happened. In less than a day, it grew 500,000 times brighter. The cloud around it ballooned into space.
It's actually relatively common for a coma, the fuzzy part around a comet, to expand large enough to be bigger than Jupiter, 100,000 miles across. But that can take days and weeks and months to build up. To have a single event, something that happened, boom, all at once, some catastrophe, to create this shell around comet homes that could be bigger than Jupiter is amazing to me.
We had never seen something like this before. In fact, the coma of the comet was actually larger than the sun itself. Briefly, it was the largest object in the entire solar system, something that was unprecedented.
Without warning, comet homes blew apart. The largest cometary explosion ever recorded. The debris stretched for 1 million miles. What caused it is still unclear.
One theory is that perhaps Comet Holmes slammed into an asteroid of some sort, creating this gigantic mega flare in outer space. Another possibility is perhaps the comet was unstable, and perhaps there was an explosion caused by expanding gas and ripped the entire comet apart. At the present time, we simply don't know.
The life of all comets hangs by a thread. Our comet survives its encounter with the sun, but it's paid a price.
Its geography has been totally rearranged. Huge chunks, mountaintops worth of rock have disappeared. An object which could be perhaps 10, 20 miles across has lost literally hundreds, perhaps thousands of tons of rock and ice on its journey.
As our comet leaves the sun behind, activity on its surface subsides.
On its outward journey, a comet gradually begins to shut down. It becomes cooler, less active, the jets begin to turn off, the coma begins to blow away, and you're left with this little ball of ice and dirt.
It returns to the depths of space, dormant once again. But the sun is just one of many challenges. Comets must also survive the gravitational pull of the planets.
Our gravity is way too small to have any effect on this comet, but Jupiter is a very large planet. It has 300 times the mass of the Earth. If the comet passes within even a few million miles of Jupiter, that can change its orbit.
The consequences can be catastrophic. In 1994, a comet called Shoemaker-Levy 9 flew too close to Jupiter. Scientists watched the planet's immense gravity tear it apart. The remains headed straight toward Jupiter.
Many people thought that the impacts wouldn't do anything to Jupiter, that Jupiter would just sort of swallow it up without a burp. And that's not what happened at all.
21 comet fragments smashed into Jupiter's atmosphere. Each impact released more energy than all the world's nuclear arsenals combined.
Comet Shoemaker-Levy 9 was not a particularly massive comet, and it wasn't even a very dense one. It actually had the consistency of cotton candy. You could have pulled bits of it apart with your fingers. But this rather tenuous little icy creature created unimaginable destruction.
The impacts hurled plumes of debris thousands of miles high and scarred Jupiter's atmosphere with dark lesions. The event rocked the scientific community.
To actually see it for ourselves, to actually see the immense destructive power by an object that's really not that much bigger than a hill was really pretty terrifying. Even though we knew the math, to see it for ourselves was amazing.
The Shoemaker-Levy 9 impact really woke astronomers up to the fact that impacts can happen now, and they can happen here.
If a comet just a few miles across hit our planet, the result would be catastrophic. Tidal waves would devastate the land. Debris would rain from the sky. Life as we know it would end. Yet comet impacts can also be a creative force. They could even trigger the birth of life itself. Across the universe, comets cause massive destruction.
They could be moving 50 or more times faster than a rifle bullet. And we're talking about something the size of a mountain. So the amount of energy that this thing would release upon impact is devastating.
But they're not always destructive. They have another side. Scientists believe they can shape entire worlds. This is Titan, the largest of Saturn's moons. It's the only moon in our solar system with a thick atmosphere. Rivers and lakes of liquid methane cover its surface. Titan was transformed by comets. Radar images reveal a moon shaped by a blizzard of comets that rained down over millions of years. Each comet vaporized when it hit, releasing gases from inside its nucleus. Gradually, they built up a rich, organic atmosphere and this strange liquid landscape. Comets turned a space rock into an Earth-like world.
Comets, in some sense, are the ultimate engineers of the solar system. Cometary impacts could give us the chemicals which give us the atmosphere, not just of Titan, but even perhaps the Earth itself.
So if comets have the power to reshape entire worlds, what part did they play in the history of our own planet? To find out, we need to get closer to a comet than ever before. We need to land on one. In March 2004, the Rosetta mission launched.
The Rosetta mission is named after the Rosetta Stone because just like the stone gave linguists the keys to the ancient language, we're hoping that the comet will give us the keys to understanding the ancient solar system.
November 11th, 2014 will be a landmark in space exploration. For the very first time, a spacecraft will touch down on the surface of a comet.
Previous missions to comets were basically flybys, and they basically give us tantalizing evidence that there was a greater mystery yet to be solved. Now we're going to land on a comet. We're going to be up close and dirty with a live comet streaming through outer space, and this is unprecedented.
Rosetta is around the size of a car. It's flying through space at 20,000 miles per hour. It's heading for this. A comet with a nucleus 3 miles wide, orbiting the sun every 6.5 years. A robotic lander will drop down to the surface, beginning the most detailed study of a comet ever attempted.
It's going to look at what the surface looks like. It's going to take samples. It's going to look at the terrain. It's going to be able to actually probe inside the comet and see what it's made of and how it's put together. We're hopefully going to learn more from this mission about one comet than we have about just everything we've known about comets for centuries.
Rosetta should answer some very simple questions.
Is it porous? Is it like a sponge? Is it like a bunch of tubes? Is it like a snowflake, you know, with this sort of fairy castle structure. These things will help us to understand how the heat flows within and maybe what causes certain portions of it to become a jet and other portions not.
But this is just the beginning. For an entire year, Rosetta will study the comet on its epic journey round the sun. Using technology so advanced, it mimics the 5 human senses.
We've got instruments that can see. We've got a kind of an ultrasound experiment, instruments that are the equivalent of your hands. So we'd like to understand everything possible about this comet's journey around the sun from when it's quiet to when it's at its most active.
But we'll have to get there first. Just to reach the comet, scientists must overcome enormous technical challenges. Rosetta must hit a target just 3 miles wide, traveling at 34,000 miles per hour. Landing on it will be even harder. Comets have very little gravity.
There's not anything that you know is going to pull you down to the surface. And there's no atmosphere, so you can't unfurl a parachute and just sail down until you touch down. You've got to figure out a way to get your lander to actually reside and rest on the surface.
Technicians have an ingenious solution. The lander is equipped with shock absorbers and a harpoon.
When it makes contact with the surface, at the same time, the harpoon will be released down into the substrate, and it will have prongs that will open that will prevent it from coming back up.
Rosetta will attempt to solve some of science's deepest mysteries.
We would very much like to know, why is it that Earth has liquid water, and so much of it, compared to any place else that we've ever seen? So how is it that the water got here? Now, there is a theory that says that comets delivered the water to the Earth long ago. But the question is, can we actually prove it?
To find out, the lander will collect water molecules to compare with water from Earth. But scientists hope to go even further. We're on the brink of making an extraordinary discovery. We may find proof that life itself has an extraterrestrial origin, that it was brought to Earth by comets. Life has existed on our planet for at least 3.5 billion years. But we still don't understand its beginnings. We used to think life originated on Earth itself, that volcanic gases and water vapor formed oceans and an atmosphere. Lightning added the creative spark for early life to begin. Now we think that's wrong, and the evidence is in space. In 1997, Comet Hale-Bopp appeared, one of the biggest and brightest comets ever recorded. Scientists found it was packed with water, gases, and carbon, the basic ingredients for life. That discovery raised profound questions.
We're all used to the idea that life originated here on Earth, and it probably did, at least complex life. But where did the building blocks come from? Where did the water that makes up our body, the organic molecules that make up the very essence of life, they actually may not have been intrinsically part of the Earth to begin with. They came from somewhere else.
Hale-Bopp suggested that the raw materials for life might have an extraterrestrial origin. Since then, scientists have found further evidence. Astrobiologist Dante Lauretta discovered that dust from comet Wilt 2 contained minerals that could only form in heat and liquid water.
We had the sulfide minerals, we had iron oxides, we had carbonate minerals, which are the same kind of materials that marine organisms use to build their shells, unlike anything we thought was possible to be formed in the early solar system.
Scientists have even found that comet Wild 2 contains amino acids.
That's incredibly exciting because amino acids are the building blocks of proteins, and proteins are essential biomolecules for all life on Earth.
These discoveries have transformed our understanding of comets. Many scientists now believe they're more than just frozen time capsules. Perhaps they play a central role in the history of our planet.
We have learned from study of a single comet and the results of the Stardust mission that they are complex chemical laboratories where the ingredients of life could form. These materials likely did not arise naturally on the surface of the Earth from processes on our planet. Instead, they had to be delivered by these messengers from the outer solar system.
The idea that we may owe our existence to comet impacts is astounding, but not everyone is convinced.
There's pretty good circumstantial evidence that a comet might have been important to life. But we don't really have, if we're CSI, if we're the comet science investigators trying to prove it, we haven't got the proof lined up yet. It's quite possible that what we have out there has nothing to do with life as we know it on Earth.
Scientists hope the Rosetta mission will resolve the issue.
If we can establish a correlation between amino acids on comets and the amino acids we have on Earth, life on Earth, that would be one of the most significant findings in science.
The story of life on Earth began 4.5 billion years ago. When our planet formed, it was a barren, hostile world. 700 million years later, the solar system plunged into turmoil. Gravity ripped comets from their orbits and hurled them in all directions, many into the inner solar system. They rained down on the early Earth for 300 million years. They released gases and organic material, creating an atmosphere and the oceans. Finally, life could begin. It's a dramatic story. But is it true?
Only time is going to tell, if we keep studying these mysterious objects, whether or not we can really pin down exactly the mechanisms and find out how it all got started.
In 100 years' time, hopefully we'll look back and say, wouldn't it be cool to have been living at that time, to be a witness, to be one of the first to make these incredible discoveries?
In the meantime, the search for proof continues.
I can't say for sure if comets brought all of these raw ingredients to the Earth and that we evolved from these materials, but it's certainly possible, and it's absolutely poetic to think that we came from out there.